Precalculus, lesson 15.2. So we're skipping lesson 15.1. It's a look at limits again, and I find that we've done just enough with limits up to this point that we don't need to do a dedicated lesson to it, or lesson for it. So 15.2 is derivatives and antiderivatives, and with derivatives, we get the first of the two main things or main tools that calculus uses. Calculus uses derivatives and integrals to do all sorts of new and amazing things with all sorts of aspects of math. And yep, so we get our first look here at derivatives, in particular derivatives with polynomials. Let me erase that little dot that I accidentally did there. And here we go. So this is 15.2. Point 2, derivatives. And antiderivatives. So let's give a little definition of what a derivative is, and then we'll look at how we find it. So derivative. We could put it something like this. The derivative of f of x, which we'll call f prime of x. So the derivative of the function f, we label as f prime. So the derivative of f of x, f prime of x, is a function such that f prime of x sub 1 finds the slope of the tangent line of f of x at x sub 1. So in other words, let's just say that like we have some function like this, okay? This function is f of x. And we have some line that is tangent to it. We'll discuss tangent in just a moment. So it touches at one point. So what we could say here is that f prime, so that this particular x value here, this x value is x sub 1. We can say that f prime of x sub 1 equals the slope of that tangent line, okay? Which one of the like face value things that this does is it gives us a tool for finding the rate of change of things. So if you have some curve that represents things like what's happening with, or a function, let's just say like a cubic function here that represents something involving like growth, the growth rate, and the growth rate went up a little bit and then down, and then something triggered it to change again. You have a function that is modeling this. The derivative would allow you to find what the rate of growth is at one particular point in time. But there's tons of other stuff that derivatives can be used for in addition to this, but that would just be one slope example. Okay, so how do you find this? Well, it starts out talking about going from a secant, oops, I want to go back to black, secant to tangent. So if we dealt with the same kind of a curve there, but I'm going to zoom in a little bit, okay? So let's just say like we're zooming in on that part of right there, and we want to find the slope like right here. Well, no, not right there. I want to go, let's just say the slope like right here, okay? Well, we could start out approximating that by drawing the secant line that goes through at 2 points. Okay, pretend that's a straight line. Okay, you could find that slope decently well. I mean, really easily because you have two different points, right? And find the slope between 2 points. How do you do that? Change in y over change in x. Well, what if we moved the point a little bit closer? So like this second point, we move closer and we found this slope here. Okay, well that would theoretically be, under most circumstances, that would be an even better approximation. Well then, what if we move the point even closer? As you move closer and closer and closer and closer, your slope is getting to be a better and better and better approximation of the slope at that one point. And well, what if you move these 2 points infinitely close together? So close together, so infinitely close together, that the distance between the 2 points is 0, or at least is infinitely close to 0, which practically speaking then, the distance is 0. Now at that point, if your 2 points have no distance between them, you now are finding the slope at that one point, and you've moved from dealing with the slope of a secant line to then finding the slope of a tangent line. So what we can do is we can call this x value, I'm going to go ahead and put some axes on this. Let's say we have this axis and this axis. Okay, so there's our x-axis, there's our y-axis. So this x value here we'll call x sub 1, and the gap between the two points, which I'll just deal with this, I'll deal with the yellow one here. The gap between the 2 points, we're going to add some value h. So this x value is x sub 1 plus h. So then what's our y value? Our y value here, well, if there's some function that we're dealing with, this y value would be, this height, would be f of x sub 1. This height here would be f of, well, what are we plugging in? X sub 1 plus h. X sub 1 plus h. Well, how do we find slope? Slope is delta y over delta x, which we could represent as y2 minus y1 over x2 minus x1, which put into these kind of terms that we're dealing with here, what's our second y value? Our second y value is f of x sub 1 plus h. Then we're going to subtract from that our first y value, which is f of x sub 1. All that divided by our second x value, which is x sub 1 plus h, minus our first x value, which is x sub 1. Now, when you simplify that, the top, there's nothing to simplify yet. So it's still f of x sub 1 plus h minus f of x sub 1 over the x sub 1 minus x sub 1 leaves you just with h. So then what do we do when we do a derivative? We say this. We say f prime of x, because we're finding the derivative, equals the limit as h approaches 0, because we're creating a situation where the distance between these 2 points is infinitely close to 0. So the limit as h approaches 0 of, now I'm not going to deal with a particular x value, I'm going to deal with just x, so it can represent any x value on my point, or on my function. So limit as h approaches 0 of f of x plus h minus f of x over h. And that is the formal definition of a derivative. This is like our method for finding the derivative function. Okay? So basically again it's just the formula for the slope between two generic points where this h is the distance from the first x value to the second x value, and we're creating a situation where we're finding the limit as that distance between the two x values is approaching 0. So what we can do is we can calculate specific derivative functions with this. So an example would be like, usually the instructions will be like, use the definition of a derivative to find, I'll say f prime of x if f of x equals, and let's go with maybe, I'm going to go with 3x squared, 3x squared minus 4x. Okay, so we're going to use this formula up here. And then again, what we'll get, f prime of x will be a new function where this new function calculates the slope of our original function. Cool. All right. So what we're going to say is we're going to say f prime of x equals the limit as h approaches 0 of, and I just like to start out, I always recommend start out with the original thing that you're dealing with, the original formula, minus f of x over h. Okay, what's that? Well, that's the limit as h approaches 0. You have to keep writing that until you actually get down to there are no more h's in it. As long as there are h's in it, you're still evaluating the limit. So what's f of x plus h? Well, we have to take our original function and plug x plus h in for wherever there's an x. So that's going to be, I'm going to put brackets because for this whole first thing, because I'm going to have parentheses inside of it. That's going to be 3 times x plus h squared minus 4 times x plus h minus, I'm going to run out of space there. Hold on a second. I was going to move this whole thing down to here. Okay, now I have room. Minus my whole function, which is 3x squared minus 4x. And it's all of that over h. So we got to do some multiplying and simplifying. So here we go. Equals the limit as h approaches 0. So again, I have to keep writing that as long as there are h's in what I'm dealing with. Until I can plug 0 in for h and I'm done. Now at this point, I can't plug 0 in for h because there's an h in the denominator, so I'm going to divide by 0. Now the cool thing is what happens is you always end up being able to factor in h out of your numerator, and that h in the numerator cancels with the h in the denominator, and what you're left with, if it has h's in it, you can plug 0 in for h at that point because you're no longer going to create a denominator of 0. Okay, so what are we dealing with here? So 3 times x plus h, well, x plus h squared is going to be x squared plus 2xh plus h squared. So we just need to multiply all of that by 3. So we get 3x squared plus 6xh plus 3h squared, okay, minus 4x minus 4h, that's that part, and then we have a minus 3x squared, minus 3x squared, minus a negative 4x, that gives us plus 4x, and I don't need that bracket anymore because I did all of the writing everything out, all of that over h. Now check it out. What cancels? My 3x squared cancels with my negative 3x squared there, and my negative 4x there cancels with my positive 4x there, and everything that's left has an h in it. So I can factor an h out, and that's what creates a cancel with the h in the denominator. So equals the limit as h approaches 0 of, I'm just going to go ahead and factor this h out, of h times 6x plus 3h, minus 4h, no, minus 4, right? 6xh to factor that out, plus 3h, okay, good. All right, so that's that, over h, those cancel. So I'm left with the limit as h approaches 0 of 6x plus 3h minus 4. I can evaluate this limit now because I can plug 0 in for h, and what am I left with? I'm left with 6x minus 4. That is my f prime of x, which again means this is a function that will calculate the slope of the original graph. So in other words, so kind of like a sub little example, find the slope of, what was my original equation? 3x squared minus 4x of f of x equals 3x squared minus 4x at, we'll say x equals 2. Okay, well, what's that slope? That slope is found using my derivative. So I can say that f prime of 2 is 6 times 2 minus 4, which is 12 minus 4, which is 8. So this parabola, when we're at an x value of 2, the slope is 8. Okay? All right, so that's how you find a derivative the long way. Thankfully, though, there's a short way. Now you have to know what's going on. You have to be able to do the long way. I could just about guarantee if you take a college level calculus class, Calculus 1, that on the final exam, you are pretty much guaranteed to have at least one question like this as a final exam question, because like this is so foundational to all of calculus. I just couldn't give you a final exam in a calculus class, in Calc 1 class, without having you do a derivative the long way. But with polynomials, there are short ways. And it uses what's called derivative rules. Let's see. Derivative rules. Rules with polynomials. Other stuff happens when you deal with like trig stuff or exponential functions and things like that. But polynomials, that's what we deal with at this point. And yeah, they're nice and convenient. Let me just show you a few and see if you can pick up on the pattern. Well, first of all, let's do the one that we just did. I'll do some examples here. So f of x equaled 3x squared minus 4x, and f prime of x equaled 6x minus 4. How about this one? If f of x equals 8x cubed, let me make that a nicer 3, 8x cubed minus, I'll make that a 6. No, yeah, minus 6x squared plus 5x minus 10. Check out what we get for our derivative. We get 24x squared minus 12x plus 5. Do you see the pattern yet? The pattern is to find the derivative of a polynomial, take the exponent, multiply it by the coefficient, and then lower the exponent by 1 power. So 2 times 3 is 6, and we write, instead of x squared, x to the first. X to the first, 1 times negative 4 is negative 4. Drop the exponent from a 1 to a 0, and x to the 0th is 1. So we're left with just the minus 4. This one, 3 times 8 is 24. X cubed instead of x, sorry, x squared instead of x cubed. 2 times negative 6 is negative 12. X to the first. 1 times 5 is 5. No x. Minus 10, you could say this is technically, minus 10. You could say this technically times x to the 0th. 0 times negative 10 is 0. So there you go. I'm just going to leave it at that. Hopefully that makes sense. Okay, let me know if you have questions. That's what's called the power rule, which, well, I could give you a few of what these rules are. So first of all, we could say if f of x equals x, I'll say k x to the nth, then f prime of x equals n times k x to the n minus 1. So the exponent times the coefficient, and then the power drops down 1. We could also say if f of x equals some constant, then f prime of x is 0. Okay. Because like what's if you have like f of x equals 5, what is that? It's a horizontal line. Well, what's the slope of a horizontal line? The slope of a horizontal line is 0 for every x value. It doesn't matter where you go on the line, the slope of a horizontal line is 0. So it makes sense that a constant would turn into a 0. Okay. Those are, yeah, that really is all you need to get by. Okay. Now we look at the big topic of antiderivatives. I say big topic as in like other main topic for this lesson. It's a much shorter topic than what we just did. Antiderivative. It's like the opposite. We say if f of x is, I'll say it like this. If we pretend f of x is a derivative, then the antiderivative which we call capital F of x. I'm going to use comma there so you don't get confused with parentheses. Is the function, it's going to sound kind of circular, but is the function whose derivative would be f of x. Okay, so the antiderivative basically finds, I like to think of it like you're going up a level to get an antiderivative from a function. And then if you take a function and you go down a level, you're finding the derivative. I think of it that way because of the powers of x. To go from a function to its antiderivative, you're going up a power. To go from a function to its derivative, you're going down a power. But yeah, so if f of x, if we pretend that it's a derivative, then we ask ourselves, well, this would be the derivative of what function? The answer is capital F of x, the antiderivative. Okay? So here's how antiderivatives work with polynomials. It looks like this, antiderivative rules. Antiderivative rules. We could say if we have f of x equals, we'll do again a kx to the nth, then capital F of x, the antiderivative, ends up being this, k over n plus 1 x to the n plus 1th power plus c. I'll explain that plus c in just one moment. And that is enough for you to get by. Because, like, here, we'll do one. Let's say find the antiderivative of, and let's say we're finding of f of x equals 7x cubed minus 8x. Oh, no. Hold on a second. Minus 6x squared plus 3x minus 5. Okay. Well, our answer is going to be capital F of x. With this kind of stuff, the capital F is mandatory if you're finding the antiderivative. If you are finding a derivative, the f prime of x is mandatory. You have to put that little, like single quote, apostrophe to make it an f prime of x. Cannot forget those details, otherwise you're communicating the totally wrong thing. Okay, well, we do 7 over 3 plus 1, so 7 fourths x to the 4th minus 6 thirds x cubed plus 3 halves x squared minus 5x. 5 over 1 x to the 1st plus c. Because what that plus c means is we're saying we don't know our original function could have had some constant. Could be plus 5, could be plus 12,000, could be minus 82.5. We don't know. There's some constant here that could have been here that when you take the derivative, the constant goes away. So this simplifies to, stays as 7 fourths x to the 4th. Our minus 6 thirds becomes minus 2 x cubed plus 3 halves x squared minus 5x plus c. So that is our antiderivative. Antiderivative at this point, it might kind of seem like, well, who cares? That doesn't seem all that practical. When we get to 2 lessons from now, super practical. And you can also check your antiderivative answers by taking the derivative of it and seeing if it takes you back to what you started with. 4 times 7 fourths is 7. Drop the power, 7x cubed, etc. Okay? And that, let me double check, but that should do it for this lesson. Yep. You might have a problem or two where you need to simplify what you're dealing with first. Like you start out with a rational function, so you have a denominator with x's in it, and simplify it to be a polynomial, then you can do this stuff. Now, what we're not getting into here, and this is where your trig stuff, or your calculus starts to take you, is it starts to take you into, okay, well, what about stuff like trigonometric functions? Like, how would you find the whatchamacallit? How would you find the derivative of like f of x equals the cosine of x? Or how would you deal with rational functions? How would you find the derivative of 3x minus 5 over x? Things like that. And then a lot more of the practical stuff that you can find using the derivative as a tool. But for our purposes, that is this lesson. Hope it makes sense and goes well.